Hey, welcome back. Today we're going to be discussing basic optimization and curve fitting, and we'll be focusing especially on the Taylor function. What are the usual problems to solve in mathematics? Well, one is to ask ourselves, how does f of x behave at a particular point, like at x sub a? Is it going up or down? Is it concave upwards or downwards? Knowing the answers to these questions help answer optimization problems. Is the point at the maximum of f of x? Is it a minimum, etc.? We need to focus on the Taylor polynomial. Studying Taylor polynomials is important for data analysis because they provide a powerful mathematical tool for approximating functions, which can simplify complex models and computations. Taylor polynomials approximate smooth functions near a point using polynomials whose coefficients are derived from the function's derivatives, allowing easier analysis, prediction, and error estimations. So focus on those last three: easier analysis, prediction, and error estimation. But why polynomials? Well, historically speaking, it's heavily used to substitute for an unknown function f of x, or a known function it's very hard to manage computationally. Why? It's very tractable to differencing and integrating, and the computations are simple since it involves integer powers. For example, for finding optimum points, we know from basic calculus that we need to find x such that f prime of x is equal to 0. And the x's where this happens are the critical points, which we denote as x sub c. For example, if f of x equals 3x squared minus 12x, then f prime of x is equal to 6x minus 12. And if we're going to equate that to 0, we find that the critical point here is x equals 2. And this is where f prime is 0. But in order for us to understand the intuition behind that, we need to take a look at the idea, this whole idea of critical points. For that, let's review the Cartesian coordinate system. Here's a graph of f of x, and they're really just pairs x, y, where f of x is equal to y. That is, there's a function f of x such that when you insert x into the function, you come out with y. For example, if f of x equals x cubed plus x plus 4, then f of 2 is equal to 2 squared plus 2 plus 4 is equal to 14, and therefore we have this pair 2, 14. So you can think of this colored graph over here as all the points of the pairs under x, f of x. Now what if we draw a line through any 2 points? Then what you get is a secant line. So it touches f of x at 2 points at x equals a and x equals b. We have f of a and f of b, and these are the 2 points which determine the secant line. Now what is the equation of the secant line? We know if we have 2 points, we can come up with the equation of a line, and for that, let's take a look at this graph over here. We'll discuss rise over run, which is really how far does the line go up is called rise, and how far does the line go forward is run. So rise over run is the ratio between the f of b minus f of a over here all over b minus a. That's your rise over run. And it looks like this. Now, that's called the slope. That's the rise over run. If we drop another line over here, call that point the variable x, f of x, then we can split this triangle into 2, and from proportions we know that f of x minus f of a all over x minus a should be the same as f of b minus f of a all over b minus a, and this gives us the equation of the secant line. A numerical example should clear this idea up better. So if we pass a line through 1, 5, and 4, 17, we have this y minus 5 over x minus 1 should be proportional to 17 minus 5 over 4 minus 1. And that gives you 12 over 3 or equal to 4, which implies that y minus 5 is equal to 4x minus 4, and finally implies that y is equal to 4x plus 1. Now, this is the equation of the secant line to the left, or in the slope format, you have y equals 4x plus 1, where 4 is your rise over run, your slope of the secant line. Therefore, what is the equation with secant line? We can just call it y equals constant plus m times x, where m is the slope of the secant line. However, what happens if we let b come closer to a? Let's make b approach a such that the distance between b and a is so small that they appear to be together. As b approaches a, the secant line will start to look like this, which is called the tangent line, because the tangent line is the slope of the curve at a. That is, loosely, it is the secant line of a and b, but b is so close to a that b actually touches a. And we know that tangent means to touch. So you can think of the tangent line as the slope at the particular point rather than the slope of 2 points that are far. It's actually the same thing, except that a and b are already touching, that it's almost the same point a. So we might as well just call it the tangent line rather than the secant line. This is the slope of the curve at the point A. And here it is an upward sloping curve at exactly the point A. So why is this important? Well, because if B is sloping upwards at A, but it's now downwards at B, it must have been flat somewhere between A and B. This means there was a point C between A and B where the slope flatlined, which means that the point might be a summit or maximum, like so. This can be very, very useful, therefore, to look for the optimum, here the maximum, by just taking a look at how the tangent line behaves as you move from one end of the curve to the other. The problem here is that if f of x is not continuous, then you have no assurance that what we showed a while ago could happen. However, when we deal with polynomial functions, this problem generally goes away. Therefore, we can use tangents to look for the maximum or the minimum given a curve. And we just use that by just taking a look at how the tangent line moves as you go from one point to the other. And if the tangent line is flat, that simply means that the slope is 0. Therefore, this points out to the idea that if you're looking for what's called critical points, as we said a while ago, we want to look for f prime of x is equal to 0. Think about stairs. If you're going up, you find a landing and then you start coming down, then going up and down, then the landing or the 0 must be a maximum. Or the other way, if the stairs were going down, get into a landing, then the stairs start going up, then the landing or the flat line must have been a minimum. So that's the whole idea. So for finding optimum points, therefore, from basic calculus, again, we need to find f prime of x equals 0. That's really the slope or the tangent line at that point. And additionally, we can take a look at how the tangent line performs over the curve, or we can take a look at the behavior of the second derivative. If the second derivative at the critical point is less than 0, or it's negative, the curve is downwards pointing, and that indicates a local maximum. Or if f double prime of at the critical point is positive or greater than 0, the curve is upwards pointing, and x sub c indicates a local minimum. Therefore, this is what it looks like. We talk about concavity. In this case, I'm just going to call it concave upwards or downwards. If it's concave upwards, f double prime of x is positive. If it's concave downwards, f double prime is less than 0. What happens if f double prime is 0? Well, that's really just a change in curvature. There's no information whether it's a maximum or a minimum. So we're really more concerned with f double prime at the critical point being positive or negative. Let's say we're given f of x equals 3x squared minus 12x. Then f prime of x is equal to 6x minus 12, or x equals 2, the critical point. And at f double prime at x is just equal to 6, a constant. Therefore, at x equals 2, the second derivative is positive. This says that the curve is concave upwards, and therefore this implies that at x equals 2, the critical point, we're dealing with a local minimum. And you can see how very easy it is to work this out since this is a polynomial. This is what it looks like. This is the curve f of x. Here are examples of the point. Just to drive home the idea that polynomials are very easy to use. Therefore, we can use it for curve fitting. So that's the next topic here, curve fitting using polynomial functions. In the previous slides, we showed how a linear function was made to pass through the points 1, 5, and 4, 17. If all we were given were those 2 points, then our equation y equals 4x plus 1 would have sufficed, and we say that we have fit the curve through those points. However, if we're given 3 points like this, this is a poor fit since our curve didn't pass through the third point. The idea here is that we want f of x to pass through all the given points. We want to really look for such a polynomial function that collocates, meaning it passes through the same points given. And the whole idea here is co and location being same place, meaning the polynomial should be at the same place where the given points are. In this case, it extrapolates poorly. So this points out the idea of a collocation polynomial. It's a polynomial that passes through all given points. However, passing through all of the points does not necessarily mean that it is a good approximation of the underlying and unknown function, because it doesn't consider the potential curvature differences between p of x and the unknown function f of x, just that they share the same points at particular places. So collocation is not enough. What we want to do is that they should share some sort of information about curvature. And here we can start talking about tangential polynomials. So to address this problem, p of x is forced to have not just the same locations, but also the same tangents at those points. So it's not only that p of a must be equal to f of a, p of b is equal to f of b, but p prime of a is equal to f prime of a, p prime of b should be equal to f prime of b, meaning they share the same first derivatives. This means that they must have the same tangent lines at the points where they collocate. And we already referred to tangents to reference the Latin to mean touch. Now we're going to extend this to more intimate functions. So at times touching or the tangent is not enough, so efforts were made to make p of x and f of x more intimately connected with a kiss. And we have osculate to kiss from os, which is Latin for mouth. In mathematics, we say osculatory polynomials because they are very, very intimate. They share higher derivatives, not just first derivatives. It's not enough that they are in the same position. They must be touching, tangent, and they must be kissing, osculate. So these are very intimate polynomials that approximate f of x, the unknown functions. So that's an osculatory polynomial, which brings us to the Taylor polynomial. This is the ultimate in polynomial osculation because it's going to share not just 0, 1, or 2 derivatives, but even higher derivatives. And this is the form of the Taylor polynomial. How is the Taylor polynomial used? Well, simplifying assumptions can be made regarding the degree of the function. For example, if third differences and up are assumed negligible, then the polynomial must be second degree or less. So we have this example. What if f prime of 1 is equal to 6 and we have this data table over here? And the differences here are the first, second, and third differences. So the 2 here is 3 minus 1, the 10 here is 13 minus 3, and so on and so forth. And the second differences is 10 minus 2, which is 8, or 18 minus 10, which is also 8, and so on and so forth. Now show that the underlying function can be modeled by a Taylor polynomial equal to 4x squared minus 2x plus 1. For this to happen, we need to take a look at the expansion of the equation that we had a while ago and plug in the numbers. So the expansion looks like this, and here we're going to assume that higher differences are 0 because third differences and up are 0. So given this, we know that f of 1 is equal to 3, so we substitute that for f of 1. We know that f prime of 1 is equal to 6, so we substitute that into this equation over here. And then the second differences are assumed to be a constant 8, and therefore we're going to assume f double prime of 1 must be equal to 8, and therefore we have this. We're going to have p of x equals 3 plus 6 times x minus 1 plus 8 over 2 times x minus 1 squared. And that reduces to 4x squared minus 2x plus 1 over here. If we have this problem, what if we wanted to estimate f of 5? Well, we just use our polynomial function to extrapolate and figure out what would be a good guess for f of x. And here, we just plug in 5 into our polynomial function, and the answer is 111. Please note that 111 is simply our estimate. We really don't know if this underlying function is a polynomial. We just assume that it is a polynomial. And if it were truly polynomial, we can say that the Taylor polynomial can do a very good job given just some information about collocation and shared higher derivatives concentrated at particular points here at x equals 1. So here we see the power of the Taylor polynomial. So what are the applications again? In summary, for Taylor polynomials, it can be used to great advantage for numerous analytical problems. And again, the most obvious is to use polynomial functions to proxy for an unknown function f of x. Another is to use the Taylor polynomial for numerical analysis problems to derive a root-finding algorithm to find the zeros of a function, aka root-finding problems. And in a way, this mirrors the kind of issues one faces with bigger optimization problems. The Taylor polynomial can also be used to derive the idea of duration for fixed income portfolios by estimating what the new price would be given how far interest rates can move from the current yield. And this ties up with the three-factor model for bond yield movements that we discussed previously under factor modeling. So for example, the price function might be thought of as a Taylor polynomial, and we can stop at second derivatives. We shall explore this ability to map out what the curve might look like given a concentration of information at some point I over here, given the price curve of a bond. And that'll be up next in our upcoming videos. Alright, so that's all we have for now. Please like and subscribe to support the channel, and see you.